Welcome back to the workshop. We want to continue taking a look at section 4.1, graphs and the representations. We've already seen kind of a really basic example that introduced us to the idea of a graph. So let's give a formal definition and then develop it just a little bit along with some definitions. So let's take a look at our notes. So to begin, a graph, G-R-A-P-H, a graph G is a finite non-empty set V along with a set E of two element subsets of V. So a graph is two sets. The first set is just some non-empty set V. The second set is a set of two element subsets. So it is a set of sets, and those sets are subsets of V. So that's its most basic definition, but actual definition, not the idea. When we go ahead and try to clarify what's going on here, we say that the set V is called the vertex set. So the elements of V are called vertices. Vertices. The singular is vertex. So you have vertices and vertex. So this is kind of like those that are familiar with a matrix, right? You have a matrix and you have matrices, so it's a little bit weird. I believe it is also acceptable to say vertex and vertexes, but it's not common. So vertex and vertices. All right, the elements of this second set, the two element subsets, are called edges. Okay, so E is called the edge set. Singular, of course, is just edge. E is the edge set. It contains the edges. So what does this look like? Well, we can identify the vertex set and the edge set for the graph that we already considered. We already labeled all of the points with letters to name them. So our vertex set isn't necessarily the dots that are here. What it is it's the letters that those dots represent. Okay, so our vertex set is H. Right, it's Holland, Grand Rapids, Kalamazoo, Lansing, Jackson, Flint, Brighton, and Ann Arbor. Okay, so our vertex set is the collection of cities, which we said was Holland, Grand Rapids. Let's see here, Kalamazoo, Lansing, Jackson, Flint, Brighton, and Ann Arbor. Excellent. That's 1, 2, 3, 4, 5, 6, 7, 8. Make sure I got them all there. 1, 2, 3, 4, 5, 6, 7, 8. Excellent. I got them all. And then we have the collection of edges which join them. So how are these edges represented? Well, the edges are just represented by the two vertices that the edge connects. So we have an edge from Holland to Grand Rapids. So we've got the two element subset H, GR, because there is an edge between Holland and Grand Rapids. Okay, so where else can we go from Grand Rapids, let's say? Well, we can go from Grand Rapids to Kalamazoo along 131, and we can go from Grand Rapids to Lansing along 96. Where else can we go? I think that's it for Grand Rapids. For Lansing, we can go from Lansing to Grand Rapids, but that's already represented. We can go from Lansing to Jackson, and we can go from Lansing to Flint, and we can go from Lansing to Brighton. That looks like it for Lansing. Let's see here. Don't want to forget that we can go from Kalamazoo to Jackson along 94, and then from Jackson to Ann Arbor, also along 94. And we can go from Flint to Brighton, and then finally from Brighton to Ann Arbor. Now, the direction doesn't matter in these cases. There is no direction on an edge. So this says we can go from Holland to Grand Rapids and Grand Rapids to Holland. This says we can go from Grand Rapids to Kalamazoo and Kalamazoo to Grand Rapids. So this looks pretty good. Let's see, I've got 10 edges there, and that looks right. Excellent. So this is my vertex set. This is my edge set. Now I can also give these slightly different names. So if we're talking about two different graphs, it's a good idea to be able to refer to the vertex set and the edge set of the two different graphs. So this might be referred to as the vertex set of graph G, okay, V of G, and this is the edge set of graph G. So now we can talk about the vertex set of graph G, or we could talk about the vertex set of graph H, whatever graphs we have, okay. The graph G itself, again, is a set of vertices and a set of edges. So G can actually be referred to as an ordered pair of the vertex set and the edge set, more commonly written as G, a graph named G, and the inputs to it are the vertex set and the edge set. Okay, so this graph, a graph with this name, with this vertex set and this edge set, that is the graph. That's its name. This is what it's defined by. All right. So that's graphs. Excellent. So we have an idea of what a graph is. This is an example of a graph. We'll take a look at some more examples in a minute, but we want to continue to build up on some definitions and basic concepts regarding graphs. So another definition for us. Whenever we have an edge E from vertex U to vertex V, we say that the edge E joins the two vertices. So this edge joins vertices K and J, for example. And the vertices U and V, we say that the edge E joins vertices U and V, and that U and V are adjacent. They're next to one another, adjacent. It is also said that edge E is incident with the vertex U, and that the vertex U is incident with the edge E. So we say that we say that an edge joins two vertices, and when we have an edge joining two vertices, those two vertices are adjacent to one another, and the edge between them, each vertex is incident to that edge, right? So adjacent describes two vertices being connected. Incident says, hey, this vertex and this edge are connected. All right, of course, we could have said V here instead, because the edge E, which connects U and V, is incident to both U and V. So we have this edge here is incident to K, and this edge here is incident to J. And K and J are adjacent to one another. Okay, so two vertices are adjacent. This edge is incident to a vertex. This edge is also incident to another vertex. Excellent. So that gives us the idea there. All right, so what we want to do next is we want to give the adjacency list. So we know what it means for two vertices to be adjacent, and we can describe all of the adjacencies given by giving an adjacency list. So what we want to do is an adjacency list, and adjacency list gives for each vertex. Okay, so for each vertex, we're going to do the thing that follows. So for each vertex, a list of adjacent vertices. So for the case of our graph that we saw earlier, this one, the one that we created, we have our, let's see, 8 vertices. And then for each of those vertices, we will list the vertices that it is adjacent to. So H, for example, is adjacent to Grand Rapids, and that's it. So we'll go through this and see what we can build up here. So let's start with H. I'm going to type these in. That would be a little bit better here. So I'm going to, let's see here. Actually, I wonder if I might be able to just slide these down. So I'm going to write it on top of here while we have it in front of us. So for example, Holland is adjacent to Grand Rapids. We can see it right there, GR, Grand Rapids. That's the only thing it's adjacent to. Well, okay, let's take a look at Grand Rapids next. This is in no particular order. So Grand Rapids is adjacent to Holland. That's already been described once, and that's okay. We would still include that here. They're adjacent, so Holland is adjacent to Grand Rapids, and Grand Rapids is adjacent to Holland, so this is fine. Grand Rapids is also adjacent to Kalamazoo and Lansing. Okay, what about Kalamazoo? Well, Kalamazoo is adjacent to Grand Rapids and Jackson. Grand Rapids and Jackson. K is adjacent to GR and J. Again, this is in no particular order, so let's go with Lansing next. Lansing is adjacent to Grand Rapids, right? Grand Rapids, Jackson, Brighton, and Flint. Grand Rapids, Jackson, Brighton, and Flint. Okay, so we have Holland, Grand Rapids, Kalamazoo, Lansing. Let's go with Jackson next. So Jackson is adjacent to, right, is connected to what other cities? Kalamazoo, Lansing, and Ann Arbor. Easy enough. All right, so let's go with Flint. Flint, what cities is it connected to by highway? Lansing and Brighton. Of course, it's connected to other cities too, but those are the cities we're concerned about here. So Flint is connected to Lansing and Brighton. Excellent. What about Brighton? Brighton is connected to Flint, Lansing, and Ann Arbor. Easy enough so far. And then finally, Ann Arbor is connected to Jackson and Brighton. And that is our adjacency list. So I'm going to go ahead and move that. You may have chosen to write that down here already, but that is our adjacency list. It's as simple as that. All right, so one more definition and theorem that I'd like to take a look at. So we're just going to start this next page here. The number of adjacent vertices of a vertex V is called the degree of the vertex and is denoted by the degree, DEG, of V. So if we wanted to, we could notice that, returning to this previous example, looking at how many cities are listed next to each city, right? Adjacency list here. The number of cities that are listed or the number of vertices that are listed gives the degree. So the degree of vertex H is 1, whereas the degree of L, vertex L, Lansing, it is connected to 4 other vertices or 4 cities in the context of our problem. So we can see that visually too. Holland has just 1 vertex coming off of it. Lansing has 1, 2, 3, 4 vertices connected to it. Okay. So one edge going to 1 vertex. 1, 2, 3, 4 edges going to 4 different vertices. Excellent. So that gives us the idea of the degree of a vertex. So finally, in a graph, if we were to add up the degrees of all of the vertices, it would actually be equal to twice the number of edges. twice the number of edges. Why is that? Well, it's because each edge, it has a vertex on either end. So that edge counts for the degree of two separate vertices. So when I add up the degree of this vertex and the degree of this vertex, 3 plus 4, this edge here contributes to the degree of this vertex and degree is 3, degree is 2, degree is 2. 4 plus 4 is 8, plus 2 is 10, plus 3 is 13, plus 2 is 15, plus 3 is 18, plus 2 is 20. The sum of all of the degrees, the sum of all of the degrees of each vertex is equal to 20. Edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? 20, which is twice the number of edges. Excellent. So that's the idea here. I think that sums up pretty much everything. The only thing that might be worth mentioning beyond this is that sometimes, so as a note here, n is given as the let's see here. Actually, we don't usually use n. A lowercase v is the number of vertices. I think sometimes that's an n, and then e is the number of edges. That might come in handy at times. So if you see that all right, so let's call that good for now. We're going to take a look at some other ideas with graphs. So we know what one is. We're going to continue talking about them. So I'll see you guys back in the workshop for another video very shortly.